So you've learned about the partial trace operation that lets you start from any state, pure state or density matrix, over any number of systems and lets you compute the reduced density of the state on a subset of the systems that the original state was defined in. So this is a very important operation that we'll use repeatedly throughout, but it's also a complex operation. It involves a lot of calculations and it's not always easy to determine what is the reduced density. So in this example, we'll work out a case that often arises and try to see how we can make our life easiest possible. So let's imagine that we have a pure state on two systems A and B and see how we can compute the reduced density on A. So the example that I want to show you is a 2-qubit state, psi AB, which is defined as root 1/3 times 0 on A, tensored plus state on B, plus minus on A, tensored minus on B. It's our state, and the goal is to compute the reduced density Hoe on A. And we've seen how to do this. We can choose any basis we want for the B system, measure the B system in that basis, and compute the reduced density on A as the average over the measurement outcomes of the measurement that was performed on B of the resulting post-measurement state. So we have to choose this basis in order to measure the B system, and that's what's the most important thing that you have to do, is find the easiest basis. For instance, here we could think, well, let's use the standard basis because that's the basis that we're used to. But that's not adapted to our problem because you can see the B system here. I already wrote it for you in a nice, convenient way. It's either a plus state or a minus state. So it makes sense that if we want to work with that state psi AB here, and we want to think about the B system, we should use the Hadamard basis. In fact, in a subsequent lecture, you'll see that every pure state can always be written in a form like this, where the registers for A and B are initialized in a basis. Note that here it's not the case for the A system, right? We have a 0 and a minus. These are not a basis, they're not orthogonal states. So let's choose our basis B to be the Hadamard basis, plus and minus on B. And let's measure B using the associated POVM elements. So we can choose two POVM elements, M plus, which would be the identity on A, tensored the rank 1 projection on plus for B, and M minus, which would be, again, the identity on A, tensored rank 1 projection on minus for B. And because this is a projective measurement, we can take as cross operators the same as our POVM elements. So now let's compute what the distribution on outcomes is and what the post-measurement states are. So the probability that we obtain a plus, this would be the trace of M plus psi. And you see what M plus does, right? It simply looks at the second qubit, projects it on plus, and on the A system, it does nothing. So when you compute the overlap of psi on M plus, only the plus part is going to stay, and what you'll end up with is probability. This here is going to be equal to psi M plus psi, and you'll get 1/3. Similarly, if we compute the probability of obtaining the outcome minus, then we do the same calculation, and you'll see that this probability is 2/3. That's pretty easy to check. And then the next thing we want to do is compute the post-measurement states. So let's compute them. We have the state Ho plus, which is equal to E plus psi E plus, divided by the probability of getting a plus, which is 1/3. And here again, you know what E plus is. It just projects B onto plus. And if B is projected onto plus, A is in the state 0. So what we get with these 1/3 cancel out, and we simply get 0 for A, tensored the plus state for B. Similarly, if we compute Ho minus, we can do the same calculation now with E minus, and we'll get minus on A, tensored minus on B. Now here we have our two post-measurement states, and that tells us what the reduced density on A should be. The conclusion is that Ho A should be, with probability 1/3, we get the reduced density on A that we had when we obtained the outcome plus, and with probability 2/3, we'll get the reduced density on A that we got when the outcome was minus. So this gives us 1/3 times 0, 0 plus 2/3 minus minus. So that's the reduced density on A. It's the final answer to our problem. and see how it was obtained, right? What was important is to choose the right basis for the B system. So once we chose the basis, we measured the B system, and if we got a plus for B, the probability of that happening was 1/3, so the squared norm of the corresponding vector on A. And if we got plus, A got projected into 0. And then, I'm sorry, I realized I made a little typo here. Forgot to write the 2/3 amplitude. So let's have a 2/3 here. And then if we obtained a minus, it for Alice was projected down to a minus, and this happened with probability 2/3. So this is a general rule. In general, if you're able to write your state psi AB in the form sum over I of, let's say, root pi ui tensored vi, right, in that form, where the ui's are anything, the root pi's are anything, but the vi are a basis for the B system, that is important, crucial condition, then in that case, we now have a recipe for the reduced density. We'll use that basis to measure the B system, and you see from the previous example that the reduced density on A will simply be given by sum over I of the squares of these coefficients here, pi, times the corresponding state on Alice, on A, which is ui. So this works in general as long as we have a decomposition like this, where the V's are a basis for B. And in the subsequent module, we're going to see that such a decomposition always exists, and it's called the Schmidt decomposition.